at the basics. What is software engineering? So, when did the term software first appear? In 1957, John Turkey coined the term software as the opposite of hardware. And what is software? Software, computer programs, procedures, and possibly associated documentation, data penetration, and into the operation of computer systems. Alternative wording of software is all programs, processes, rules, and documentations are software. Software is not just code, it is also includes documentation and data relating to the operation of the computer system. Then we have what is engineering? How do engineers differ from scientists? Scientists build to learn, engineers learn to build. So scientists are just building to learn, they're just discovering stuff. Engineers learn how to build. So scientists build a prototype to study a phenomena, and engineers studies known principles in order to construct a working prototype. We have the 5 characteristics of engineering disciplines from Ludwig. Practical results, it works versus it should theoretically work. You can touch the result. Quality can be measured. Functionality is only recognized when it has proven itself. So we first have practical results, then we have cost thinking. Cost reduction as a goal does not mean generate a local optimum. This might have the opposite effect. Goal is achieve a global cost benefit ratio. Quality awareness is basic attitude of an engineer, often leads to a reduction in cost. So we have quality awareness. Then we have follow standards with discipline, standardize interfaces, terms, communication, etc. Dowell pin first standard in Germany. Thinking with assemblies standard as basis. Solved sub problems can be incorporated into larger solution. Known solution can be integrated. Can the characteristic be transformed to software engineering? We discussed this to be ready to argue why transfer is difficult. Software is tangible, you cannot touch it. Its quality is hard to measure, and characteristics of traditional engineering principle cannot simply be transferred to software. We know that when did the term software engineering first appear? In 1969, the NATO conference where F.L. Bauer coined the term software engineering. Historical build-up, computers are used more and more in military sector. Software plays a subordinate role. Main field of application is mathematical calculation. Fortran is developed for this purpose in 1957. With the development of ever faster computers used by more and more people, more and more complex programs are written. Software is being increasingly important. The consequence is that more and more errors in increasingly critical areas. What is meant by the term software crisis? The errors accumulate and lead to considerable damage. Software crisis, for example, software engineering emerged as a response to it. We know that launch of Mariner 1 rocket had to be detonated shortly after launch. A typo in the program code caused the rocket to veer off course. Then we have how did Jiskra describe the programming problem. As long as there are no machines, programming was not an existing problem. When we had a few weak computers, programming became a minor problem. And now that we have gigantic computers, programming is an equally gigantic problem. How did F.L. Bauer justify the need for software engineering? The whole trouble comes from the fact that there is so much twinkling with the software. It is not made in a clean fabrication process, which it should be. What we need is software engineering, actually. In 1970, Wilson Royce, the waterfall model, the first structured process model for software development. It gives the classic definition of software engineering. Software engineering is a discovery and application of sound engineering principles with the goal of economically producing software that is reliable and runs off real computers. Software engineering is any activity that involves the creation or modification of software insofar as the software pursues objectives that go beyond the software itself. We know that what is the IEEE definition of software engineering? The application of a systematic, disciplined, quantifiable approach to the development, operation, and maintenance of software. That is the application of application of engineering to software. We know that the study approaches. In short, software engineering is the systematic, disciplined, and quantifiable approach to the development, operation, and maintenance of software, working on software according to engineering principles. Then we get to know what is our definition of software engineering used in this course. Software engineering compromises the professional engineering style, ongoing development and operation of higher quantity, large program systems with many participants under cost and time constraints. The 4-number element of this definition are a favorite check, oral exam check, be able to recite quality, size, participant, and cost time constraints in order. For example, our definition of software engineering used in this course. Software engineering compromises of professional engineering style, ongoing development processes of higher quality. These are the four definition of software engineering. What is software engineering? And software engineering compromises of professional engineering style, which is ongoing development and operation of higher quality, large program systems with many participants, and fourth is under cost and time constraints. Then we have which discipline exists in software engineering. We have development, we have quality management, we have evolution, we have management, and then we have basic topics. Development consists of requirements, context analysis, requirements engineering, design, course granular design, architecture, detailed design, implementation. And quality management consists of quality assurance and testing, test inspection metrics, processes and process models, improvement, process model, maturity levels. Evolution consists of rollout, operation, maintenance, further development, reuse, re-engineering, refactoring, change management, management strategy, economy, team dates, risks, customer, client, contractor, innovation, etc. And the basic topic is that more or less relevant to all modules: configuration management, documentation, knowledge management, people in the software engineering process, and digital ethics tool. These are basic topics. Which design decisions belong to which development discipline? You have context analysis, benefits of software, we have product vision, we have business objectives, we have business processes, and we have requirements engineering, features, functions, quality criteria, user interface, and we have grained draft, we have architecture, for example, and we have technology, reuse, system components, detailed design, interfaces, components, implementation, programming language, and deployment. These are design decisions belong to which discipline. We have context analysis belongs to this, requirements belongs to this, and just like we mentioned others. Which development results and test level belongs to the discipline. Downwards the system is decomposed, disassembled, detailing. Upward it is put together again. Integration and quality assurance. Each discipline is paired with a result and checked by a test level. Context analysis is system used, acceptance test, operation. Requirements engineering is usable system, usage test, system test. Architecture is integrated system. Detail test is integrated subsystem, integration test. Implementation is implemented component, unit test, component test. Then we have learning objective. Assign the activities in the software development process to associate design decisions, development results, and test stages. Practice reproducing the full three-way mapping. We have question 14 and 15, which leads to this mapping that we have. First, context analysis, requirements engineering, course grained draft, architecture, for example, detailed design, implementation. Then we have context analysis, which system we used. Then we have requirements engineering, we have architecture, we have detailed design, we have implementation. Challenging in software engineering. The first challenge is basics of communications. What can go wrong? Communication and the quality of the foundations are important success factors for software development projects. Real projects show how badly this can fail. For example, electronic health card, one of the largest ID projects in the world, a 2005 supplier claimed we will be able to make an offer that won't have to be changed much after. By 2018, technical requirements changed more than 150 times. After 14 years of planning and 1.2 billion euro, the card was close to being cancelled. Otto Group cancels IT Mega Group 2012, introducing central standard software for the entire group turned out to be too complex. We have challenge 2, complexity. Why is complexity a problem? The big is not multiple of something small, but something completely different. Solutions for small problems cannot be scaled for large problems. This is according to Ludwig, that if you have a solution for small problems, you cannot scale it to big problems. From Ludwig, that building a high-rise building is not the same as building a carport 10 times over. Instead, it is completely different. The requirements, effort, and construction are completely different. So if you're building a small thing and you build it perfectly fine, you cannot just upscale it for bigger solutions, because you cannot do it. The requirements, the effort, the constructions are completely different. So the big is not a multiple of something small, but something completely different. Growing team size brings new problems, dimensions, communication, organization, tools, comprehension versus complexity. The naive expectation is that comprehension declines gradually as complexity grows. So comprehension declines, so you cannot understand it that much as more complex as it gets. Actually, it collapses much more steeply, curve drops almost vertically. Then we have the third challenge, global optimum. What does it mean and why is it hard? The goal is to achieve a global optimum. Does not mean that it is sufficient to achieve optimization in the individual areas. A global optimum means looking at the context from a holistic perspective, and this is neither easy nor done quickly, but it is necessary in order to avoid unfavorable local optima. We want to optimize costs and omit the test. A quality problem will probably arise, not a global optimum. For example, we want to optimize performance. Maintainability will probably suffer as a result. So if we optimize performance, maintainability will suffer. So we have a global optimum, and what does it mean and why is it hard? So the goal is to achieve global optimum does not mean that it is sufficient to achieve optimization in individual areas. A global optimum means looking at the context from a holistic perspective, and this is neither easy nor done quickly, but it is necessary in order to avoid unfavorable local optima. We want to optimize cost and omit test, for example, or a quality problem will probably arise, not a global optima. We want to optimize performance. Maintainability will probably suffer as a result, etc. So it's not that you do something and then nothing. There's no effect. There's always a counter effect to something. So you optimize performance, then you have to look into maintainability. When you optimize cost, then you omit the test. Then the quality will be probably a quality problem will arise. The chain is only as strong as its weakest link. So if a single discipline is neglected, the software engineering chain breaks. So if you have multiple disciplines in software engineering, a single you neglect, then the chain is breaked. That's global optimum. What characteristics project-based software engineering? So the origin is dominated in 70s. Development of customized software. This is the origin. There is a client customer who decides on the functionality of the system for an external customer. Legally binding contract. Requirements are implemented on the basis of the customer's problem. If the problem changes, the software must be adapted. Customer pays for the software and its further development. In cases the software has a long service life, the customer generates the requirements. Customer rarely manufacture which are implemented in the software, which, for example, the manufacturer, which in turn solves the problem. Then we have what characteristics product-based software engineering. More and more standard software leads to new approaches in software engineering. For example, the origin starts from development of standard software. Example is applications. There are many users but no client customer. The software manufacturer decides on product strategy, features, platform, etc. Requirements arise from the potential need of future users. Development costs are spread across a large group of users. Customization costs may arise, of course, because a standard solution does not fit. The manufacturer decides on service life and further development, when which content is added, or even when product development is discontinued. So we have rapid market launch can be a success factor. For example, that excellent products can fail if a lower quality product is launched earlier. So users are less like to switch if they have invested time or money in a first product. The triangle is that a need, manufacturer, inspires requirement, features, manufacturer, which are implemented in the software, for example, which is us, the developer, which realizes to fulfill the need. We need to name the differences. Who defines requirements? Customers versus manufacturer. So we know that requirements are described by manufacturer. And who pays? Customer versus many user. Who controls service level, and the role of time to market in product-based software engineering. So model, I repeat a section of the software depending on the context. I abstract from certain details. Examples are specification, diagrams, and metrics. Artifact, I am a tangible piece of information that is created, modified, and used by people when they perform activities. I can be a model element, or document. For example, document, requirement specification, object-oriented analysis model, or C++ program. Tool, I am there to carry out work that, at least in principle, could be done without me. However, I am no longer included in the end result. So what is a taxonomy? A taxonomy is a schema that partitions a body of knowledge and defines the relationship among the pieces. It is used for classifying and understanding the body of knowledge. Taxonomy is the basic ingredient of a mature discipline. The lecture shows botany taxonomy as an example. What are taxonomies and definitions of terms particularly important in software engineering? Tool and end product are language. Language is ambiguous by definition. This makes it all the most important to define terms and use them consistently. Always create a glossary to define terms and develop a common understanding within team. This is the core principle of domain-driven design. Then we have lecture go-to summary. So software is not just code, it includes documentation and data related to the operation of a computer system. Characteristics of traditional engineering disciplines cannot simply be transferred to software, of course. Software engineering is a comparatively young discipline that originated in the 1970s. It emerged as a response to the software crisis that was declared at the time. Software engineering compromises the professional engineering style for the development and operation of high quality large program systems with many participants under cost and time constraints. And we have different disciplines have emerged that focus on human, methodological, economic, or even ethical aspects. The challenges of manufacturing high quality products are high. Communications and the quality of the foundation complexity of the domain to be mapped. Solutions do not scale with size, and finding a global optimum.